Swayam Prabha. Digital India. Educated India.
With this lecture today we are going to start the second module of this course. So, in this module we are going to study the wave solution for continuous systems in one dimension. Now, why should we study this wave solution, or what is commonly known as the Alembert solution? So, to look at the reason, let us make a quick recapitulation of what we did in modal analysis of continuous systems. So, let us consider the case of a string. So, what we had was this equation of motion and the boundary conditions. Now, we search for a solution which has a very special form. So, consider this equation of the string along with the boundary conditions, fixed boundary conditions. So, what we have done, we have considered special solutions of this equation and the boundary conditions. So, here I show this equation of the string and the corresponding boundary conditions at the two ends. Now, we assumed a solution which had the structure like this. So, we had a space dependent amplitude function multiplied by a harmonic function which is in the complex form, and we can take either the real part or the imaginary part or a combination of these two parts, as we have already discussed. For the problem of the string, for example, this is a self adjoint problem as we have discussed. So, W, the amplitude function, is real, and so we have a solution which can be which we wrote as a combination of the real and the imaginary parts of exponential I omega t. Now, we substitute this solution form in the equation of motion, and what we obtained was the eigenvalue problem. So, the eigenvalue problem consisting of the differential equation as is shown here and the corresponding boundary conditions. Now, for this eigenvalue problem we have a general solution which has a structure like this. So, now with this solution we are going to put this solution in the boundary conditions. So, when we substitute the solution in the boundary conditions, we obtain this vector equation. So, we have a matrix multiplied by this coefficient vector d h, and that must be equal to the 0 vector. Now, for non trivial solutions for d and h, we put the determinant of this matrix, to 0, and that gives us the characteristic equation which we can solve for the eigenvalues, and putting back the eigenvalues in this vector equation, we solve for d and h, we have the eigenfunctions. So, the point to note here in the modal analysis is that we obtain the eigenvalues and eigenfunctions when we have boundary conditions. So, the boundary conditions this and this. So, in our original equation these are the boundary conditions. So, if we do not have boundary conditions, then what happens? So, there can be many situations where we may not have boundary conditions, or the boundaries are so far away that we can consider for short time intervals that this system is infinite. So, for systems of infinite extent, therefore, we do not have these boundary conditions, and therefore, we do not have modal solutions for such systems. So, which means we do not have eigenvalues and eigenfunctions, as we have discussed in modal analysis. And remember that in most of the approaches that we have discussed till now, we have used this modal expansion for solving the system, for initial value problem or force vibration problem. So, for various kinds of problems, we have used the modal expansion for solving the problem. Now, once we do not have these modes, the eigenfunctions in the conventional sense, how do we go about solving the system? So, what kind of solutions should we expect for such systems? Now, in the course of our discussions, we also came across a problem in which we did not find eigen values. So, this is a system that we have discussed before, in which a fixed bar and the free end of the bar is connected to a damper which is fixed to the support. Now, we have this equation of motion and the boundary conditions as shown, and for this problem remember that we obtained a characteristic equation. So, this was the characteristic equation where this gamma is related to the eigenvalue of the problem S, and A is a constant which is defined in terms of the speed of propagation of axial waves, the damping, and the material properties and geometry of the bar. Now, you see that when A equals 1, there is no value of gamma for which this characteristic equation can be satisfied. So, it must be minus infinity. So, there is no finite value of gamma. We will say that there is no existence of an eigenvalue when A equals 1, and A equals 1 when this damping coefficient D takes on this very special value E A over C. So, for this problem we did not have eigenvalues. So, this is another problem where and it is very similar to the problem of an infinite system or semi infinite system, for which we do not have this eigenvalues and eigenfunctions. So, what we find is that there are situations where you may not have, or the modal solution does not exist because either the system is infinite or because of very special situations or parameters in the system, the eigen values do not exist. Then we also discussed the case of a travelling string. So, if you look at the travelling string, then we had the solution of the the general solution that we obtained in our previous discussions. We obtained a general solution which looked like this, what I have put on this slide. So, here you can see that the space part and the space and the time, they are not separable as we have seen in the modal solution. So, even if you take one of the modes, say for example n equal to 1, then also you will see that this is not separable, the solution not separable, which is not the case for say the static string. So, here we said that this problem is non self adjoint and the solutions are of very special type. So, let us look at the solution for n equal to 1. I have put this solution for n equal to 1 and V over C as 0.4. So, you can see that the characteristics of the modal solution that we have all discussed in the previous lectures. So, that is not there. So, you cannot, for example, the string does not pass through the equilibrium point, all points of the string do not pass through the equilibrium point at the same time. So, there is a propagation of there is a propagation of disturbance that you can possibly see in this. Then 2 points of the string are neither they neither have phase difference of 0 or pi. So, that was another characteristic of the modal solution that is missing in this solution. So, this is another example. So, but this is a finite system, this system is finite, yet we see that our solution does not satisfy even for this a single mode, the solution does not satisfy the properties of the modal solution. Then we looked at in the forced vibration problem, if you recall, we looked at the string with a travelling force. So, there we observed in the solutions a very strange kind of behavior. So, let us look at it once again. So, this is the string on which a force is travelling at a speed v. So, here I show you the one of the solutions that we have discussed before. At a low speed, the force is travelling at a low speed 10% the velocity of transverse waves in the string, and you will find the string has a very strange kind of motion which looks like discrete. It remains almost it remains static at a certain configuration for some time. Certain portions of the string remain static at a certain configuration, unless a kink which brings in a new configuration changes the angle of the string or the solution or the deflection. So, if you look carefully, then you will find that there is a kink which is travelling back and forth in the string. So, these are some. So, this is another another situation where you find that the solution there is a transient, there is a propagation of information back and forth in the string. Another example, we have again discussed this example before in initial value problem, where we talked about initial velocity conditions. So, let us look at this once again. So, we have considered a string with initial conditions as shown here. So, initial displacement was 0, initial velocity was given a distribution like this. So, in the central 1/5 portion of the string, we have this velocity distribution like this. So, this is the velocity distribution, displacement is still 0, but the velocity is distributed like this. And let us look at an animation that we have seen before. Once this velocity condition is given. So, you see that there seems to be a propagation of fronts in two directions, which go and hit the wall and then seem to come back and repeat itself. So, this is another example. So, all these are so in the time scale that we are looking at. So, these behaviors are transient behaviors. So, we have looked at various examples in which we find that the motion of the system is in terms of propagation of waves in the system. Now, let us look at the modal solution of a normal taut string, which looks like so. So, what we have seen is we have so we have in all these examples we can understand the behavior of the system when we look at the solutions in terms of travelling waves. So, our motivation comes from these examples in which we find that either the eigen frequencies do not exist, or we find that there are the solution is very strange in terms of travelling disturbance, and these solutions are also very important, or this kind of behavior is also very important in studying let us say defects in materials. So, if there is a wave propagating in a structure or in a material, then if we understand how the wave interacts with the boundary or with internal defects, for example cracks etc., or different phases in a material, then we can say many things about the material or the structure. So, from various all these points of view, we are motivated to study the wave propagation solution for continuous systems. So, we would like to study the solution of a continuous system in terms of propagating waves. So, let us look at the example. So, let us consider the wave equation. So, what we are looking at is this wave equation, and we want to find out or determine the solution of this equation in terms of propagating waves. Now, so to do that, let us write this equation like this. So, you see this equation can be, so let me write it first. In terms of this operator. Now, this operator I can factor. So, I can factor this operator like this. Now, for solution you so you can easily see that I mean this equation is satisfied whenever this or this is satisfied. So, let us first look at this equation. Now, you will find that this solution of this equation can be written as so if w x comma t is some function, any function f z, z replaced by x minus c t. If you substitute this function, of course, it has to be differentiable. So, if you substitute such a function here, then you find that this satisfies this equation. This can be easily checked by substituting here. Now, what is this solution? So, let us visualize this solution. Suppose you have f z, the function f z of this form, let us say. Now, what happens when I replace z by x minus c t and let me plot with x rather than so this so here I am replacing z by x minus c t and I am plotting with x the function at different times. So, let us say at time t equal to 0, at time t equal to 0 I have f of x. So, which is same as this. At a certain time, what will happen? Suppose t equal to let us say 1 over c. So, what we have at t equal to 1 over c is f x minus 1. So, now I have to plot f of x minus 1. So, therefore, you find that the value at z equal to 0 now occurs at x equal to 1. So, therefore, this pulse has moved a certain distance towards the right. In time 1 over c, and it has moved a distance of 1 unit. So, this let us say this peak, if you track the peak will be same as this. So, this is 1 unit. So, it has travelled a distance of 1 unit in time 1 over c. So, the speed of propagation is 1 over c, which is c. So, the speed of propagation of this pulse is c. Thus, we observe that this solution represents a travelling pulse or a travelling wave in the positive x direction, at a speed c. So, this is the reason why the c in the wave equation, this same c as in the wave equation, is known as the speed of propagation of the wave. So, this is travelling at a in the positive x direction at a speed c, and that is a solution of this differential equation. Similarly, if you look at this differential equation, then the solution by the same argument you can find is given by g of x plus c t. So, in this case the function or the wave pulse which is represented by g of z now travels in the negative x direction. So, these are the two solutions of these two differential equations. Now, it can be shown that the general solution of the wave equation can be written as f of x minus c t plus g of x plus c t. So, we have the general solution therefore, is a superposition of two opposite travelling waves as shown here, and both of these waves are travelling at the same speed c. Now, let us look at this situation. So, this represents x, this represents time t, and this is the displacement or the field variable. Now, so at time t equal to 0, we have this solution. At a certain time instant, let us say if this is if this is the positive travelling wave, which means it is moving in the positive x axis direction, then this situation looks like this. At yet another time instant, the pulse has travelled forward. So, if you now track so, this is the line on which let us say the crest of this pulse is travelling. Similarly, this is the line at which this boundary of this pulse is travelling. So, we can draw what is known as a space time diagram and in this diagram suppose this point was the maximum amplitude point here. So, x 0 let us say. Then this line tracks the peak of the wave, and the equation of this line is given by this. So, this line is known as the characteristic of the wave equation. Similarly, it will have another characteristic for the negative travelling wave. So, this is another characteristic of the wave equation. So, when we have both these two components in the solution, we have a positive travelling wave and a negative travelling wave, and the net solution is the superposition of these two solutions. So, you can so, this diagram is known as the space time diagram, and the solution at a certain point therefore depends on how these two waves, the opposite propagating waves starting from t equal to 0 reach this point. See, this point is at a certain t and at a certain space location. So, this is known as an event. So, the solution here will depend upon So, these are the two characteristics, one is of the negative travelling wave, the other is of the positive travelling wave. So, we will see very soon that the solution at a space time point depends on the conditions. So, these are the initial conditions. So, at t equal to 0 what we specify are the initial conditions. So, the solution at this point in the space time diagram will depend upon the initial conditions given in this interval. So, so if this is x 0, then this is x 0 minus C t to x 0 plus C t. So, we will when we determine the initial value when we solve the initial value problem in terms of propagating waves, then we will find that the solution at this point is dependent upon the initial conditions specified in this interval, not what is outside this interval. So, so in this space time, in this space time diagram we can visualize various things. Now, this solution that we have written out so this solution is known as the Alembert solution. So, this is the Alembert solution of the wave equation. So, this structure tells us or clearly shows that we can think about any solution of the wave equation in terms of positive and negative travelling waves. So, let us see then the modal vibration of a string. Now, we consider a normal taut string with fixed boundaries, and we have obtained the solution let us say in this form. So, here so this is the what is known as the kth mode, and we recall that the circular natural frequency of the kth mode is given by k pi c over L, and this is the corresponding eigen function. So, this product can be easily written using trigonometric identities. So, this modal solution for the kth mode can be written can be expressed as a superposition of these two solutions. Now, here immediately we can recognize that this is a this is the positive travelling wave and this is the negative travelling wave. So, we can decompose this stationary wave solution in terms of travelling waves as you see here. So, in this animation here you can see this decomposition. So, you find that so this here I have shown the second mode of a fixed string, and I have also shown the propagating waves which are written below. So, for a and the black curve shows the actual configuration of the string. So, you can see for example, so this if you follow this crest, then this is a negative travelling wave and there is a positive travelling wave, this is the positive travelling wave. Now, these two waves do not satisfy the boundary conditions as you can see, but their superposition does. So, the superposition is shown in black. So, so like this you can understand various modes of the string as superposition of two travelling waves, one in the positive direction, the other in the negative direction. And these two waves do not satisfy the boundary conditions as you can see. Now, how are these waves, these travelling waves, what we are decomposing in, how do we understand this the existence of these travelling waves? So, for that we have to look at the solution in detail, and which we will do very shortly. So, let us recapitulate what we have studied today. We have looked at the travelling wave solution of the wave equation, and we have looked at why we are studying this travelling wave solution. So, what we have mentioned is that there are various possibilities or systems in which the eigen values do not exist, for example, for an infinite system or a system in which the disturbance has not yet reached the boundary, maybe there is an obstacle or there is a crack or a discontinuity in the material, at which the propagating the propagating wave will have certain interesting characteristics, or it will show certain interesting characteristics. For example, from a boundary, as you have seen in the case of the initial value problem, that the wave front propagates and reaches the boundary, and then there is a reflection back. So, if we understand these interactions of the disturbance with boundaries, with inclusions or cracks or discontinuities in the material, then we can evaluate the structure or the material. So, this is one reason why we are studying these wave solutions for of continuous systems. So, and this provides us with a very strong motivation for studying the wave solution. So, we are going to look at the initial value problem in terms of the wave solution in the next lecture. So, we conclude this lecture here.